Okay, in our last problem, an in-class problem, we worked through the titration of a strong acid and strong base and went through 4 different points in the titration: before it begins, before the equivalence point, at the equivalence point, and after the equivalence point. We're going to continue that theme now and do one of the weak-strong combinations. In this case, we're titrating a weak acid in our flask with a strong base that's in our burette. So we need to calculate the pH during the titration at 4 different points. And one of the important things that we want to make sure that we know how to do is figure out where the equivalence point is, because that's going to help make the calculations that we need to do a little bit more straightforward. So before we even start doing the calculations of the pH at different positions, I want to run through how to calculate where the equivalence point will occur. And I'll show you with this problem. It's actually something that we could just do by looking at it, but then we'll actually run through the calculations of how that occurs. So for example, here we've got 0.1 molar sodium hydroxide in our burette and 0.1 molar propanoic acid that's in our flask. So because these concentrations are the same, the volumes to get to the equivalence point will be the same. So I can already see that the 40 milliliters here is going to be my equivalence point. So that was something that we could do in our head. But I want to show you the calculation for how you'd work through this and see that you'll still get to the same 40 milliliter answer. And the idea is when we are at the equivalence point, what that really means is the moles of analyte reacted is equal to the moles of titrant added. And so the analyte is, again, what's sitting in our Erlenmeyer flask there, and the titrant is what's sitting in our burette. And so when the moles of each of these have become equivalent, we've reached the equivalence point. And so our analyte, again, in this case, is propanoic acid, and our titrant is sodium hydroxide. Remembering that the sodium ion is a counter ion, it's really just OH minus. So what we have to do is figure out how many moles of HPR we have, and then we'll have to have an equivalent number of moles of OH minus. So again, let's walk through and just go through this calculation here. So if we've got 0.1 moles of HPR per liter, again, this is the concentration of our analyte. If we multiply that by the 0.040 liters, again, this is the volume of our analyte, this is going to equal the moles of our analyte. And again, our analyte is HPR. So units will cancel here. We'll be left of moles of HPR, which is our analyte. We again can take 1 mole of HPR and 1 mole of OH minus, and we can get this from our equation stoichiometry. So probably what I should have written down first, so we'll write it down here, I didn't write it down at the beginning, was actually what the chemical equation is for what happens in this titration. And that is, we have our analyte HPR that is in our flask, and when it encounters hydroxide from our burette, this hydroxide, being a strong base, is going to rip a proton off of our HPR. Chemistry is shown with a one-way arrow, generating water, and then our conjugate base. And so the stoichiometry of this is 1 to 1 to 1 to 1, so that 1 mole of HPR will react with 1 mole of OH minus. So that's where we get the stoichiometry. And I know that there are 0.1 moles of OH minus for every 1 liter. So again, this is the concentration of our titrant, and this will equal 0.040 liters, again 40 milliliters. That is the volume of our titrant. So for this problem, it really was very simple from a calculation standpoint. These concentrations will cancel numerically, so all we're left with is the same volume of analyte. one of the things I wanted to point out is this is really kind of equivalent to an MV calculation. So like an M1V1 equals M2V2. Even though we use that for dilutions, conceptually it's the same because we have to have the same number of moles here. And again, it's related by this equation stoichiometry. For the most part, what we're going to see with this kind of chemistry is all of the stoichiometry is 1 to 1 to 1. So mathematically this will not matter, but I want to make sure that people understand that this is important, because particularly as we get into our last section in this chapter, which is on solubility, where the ions are not always present in a 1-to-1 ratio, this will become important. All right, so that was kind of a preliminary piece to let us think about where the equivalence point is, because this problem didn't list what's going on here. Clearly we can see that when we're at 0 milliliters, this is before the reaction begins. When we're at 30 milliliters, since the equivalence point is at 40, this is before the equivalence point. 40 milliliters is at the equivalence point, and 50 milliliters is after the equivalence point. So we have the same 4 points that we talked about for our strong acid, strong base titration, but again with a weak acid, strong base titration, we're going to have, again, a point before we begin, right here, some point before the equivalence point, at the equivalence point, and after. So like we did with our strong acid, strong base, as we work through each part, we'll kind of come back to our cheat sheet here and see how it all kind of fits in. All right. So you will probably see a problem on quizzes or exams that kind of relate to calculating what the volume is to the equivalence point. Another way that we can use this calculation is maybe you know the concentration of materials in your burette, you know the volume of materials in your flask, and you know the volume of titrant that you deliver to get to your equivalence point. So in that way you can figure out the unknown concentration of your analyte. That's typically how titrations are performed. Okay, so we're going to work through, again, parts A through D here. And as it says here, part A is before the titration begins. We've added 0 milliliters of our titrate. So we're going to use the same sheet and these same kind of questions to kind of walk through what's going on here. And so what we have here for the first part, if we think about who's there, we really only have HPR in solution. We've got HPR in solution. It's 0.1 molar, and I'm going to drop my zeros right now. I'm going to understand that they're there from a significant digit standpoint, but I'm just not going to write all of them out. And we've got 40 milliliters. So at this point, this kind of becomes like a chapter 18 type problem. We just have a solution of a weak acid. We need to figure out its pH. We actually don't need to use the volume here for this first part, because whether we have 4 milliliters, 40 milliliters, or 4 liters of the solution, the pH is going to be the same. So we need to think about chemistry. No chemistry yet. We haven't started our titration. Haven't started our titration. No volume change yet. And again, we'll just put a little note here. The 40 milliliter volume doesn't affect pH. Whether we have 40 milliliters in our flask, 4 milliliters, or 4 liters, that's not going to change the pH of our starting solution. But we will use an ice table to figure out what the pH is of that starting solution. So let's think then again about how we did this in chapter 18. Well, if you have HPR in an aqueous solution, some of those HPRs will be able to give their proton up to water and then leave behind the conjugate base. We can use an ice table to figure out exactly how much H3O plus dissociates. So 0.1 molar. Water is not part of our equilibrium. We're going to assume no other contributions of H3O plus or PR minus from any other circumstances or situations. Propagate our change column with variables, 0.1 minus x, x, and x. Again, let's just do a quick little pre-check here to make sure any assumptions would work. Our pre-check is going to take 0.1, which is the concentration of our starting material, and divide by Ka, which in this case the Ka for propanoic acid is 1.3 times 10 to the minus fifth. This equals 7,692. Clearly greater than 400, so our check is okay. Ka then is equal to 1.3 times 10 to the minus fifth, and that's equal to x times x. I'm going to make my simplifying assumption, so 0.1. Solve here for x. X is equal to 1.14 times 10 to the minus 3, and that's equal to our H3O plus concentration. Negative log of that will give us pH, and that's 2.94. Okay, I went through that kind of quickly, so if what I went through was a little bit confusing, maybe go back to chapter 18 and look at the sample problems for figuring out the pH of a weak acid or a weak base solution. Okay, using an ice table for that, using a pre-check, solving for x, and then your pH. So again, if that was a little bit quick, make sure to look at some earlier sample problems, because at this point in working through our titrations, we're going to work through these worksheets fairly quickly. So again, that was part A, figuring out the pH of our starting solution, and that was 2.94. Let's look at our kind of cheat sheet here and see that we followed what we were supposed to do. If we're before the titration begins, we need to simply use an ice table and the Ka value to determine the H plus concentration from the dissociation of HA. So that's what we did. Our X was equal to the H3O plus concentration. And then once we have the H3O plus concentration, which is related to the amount of acid that dissociated, negative log of that will give us pH. Pretty straightforward for part A. Okay. Part B says, let's figure out what's happened after we've added 30 milliliters of our titrant. Okay, walking through the solution, this worksheet here, thinking about who's in solution. So again, going through this worksheet fairly quickly because hopefully we're getting proficient at this. We've got HPR, it's 0.1 molar. We've got 40 milliliters, which means there's 0.004 moles of HPR. We've added sodium hydroxide to solution, which means there's Na+, which we're not concerned about because it's a spectator ion, and OH-. The OH- is significant. It's present at 0.1 molar. And if we add 30 milliliters, that means we have 0.003 moles of that in solution. The chemistry available, if we look at who's in solution, there are 3 species in solution: HPR, Na+, and OH-. Since Na+ is a spectator ion, the only option we have is to react HPR with OH-. So that's the chemistry equation that we'll write. HPR plus OH-. Again, this strong base is going to rip a proton off of our weak acid. So here's our strong base, weak acid. We generate water, and then we leave behind the conjugate base. So one of the things to notice, if you ever saw a problem where you had HPR in your flask and you tried to do a titration with HCl, H+ would be the only thing that's relevant in solution here, and we really would have no chemistry happening because you won't have H+, which is a strong acid, reacting with a weak acid. You have to have an acid and a base reacting together to do chemistry. We again use an ICF table to propagate our chemistry amounts, 0.004, 0.003. We're not concerned with water that we produce, and at this point we're assuming that there's no PR- from any other sources. Our limiting reagent is the hydroxide because this number is smaller. So we're going to lose all of our limiting reagent as our reaction begins. We're going to lose the same amount of our weak acid and gain the same amount of our conjugate base. So what we have left when the reacting has been completed is 0.001 moles of HPR and 0.003 moles of PR-. So what makes titrations different from just reacting some hydroxide, say from solid sodium hydroxide, with HPR like we did in sample problem 19.1, is we have 2 volumes that are mixed together. So we need to consider the fact that the new volume is now 70 milliliters that we have in our flask. And that's going to change the concentrations that we have of these. So again, if we take and put each of these into new concentrations, it's going to be equal to the number of moles that we have divided by the new volume. So 0.001 moles divided by 0.07 liters, that's equal to 1.43 times 10 to the minus second molar for the new concentration of HPR. The new concentration of PR minus is equal to 0.003 moles divided by 0.07, and that's equal to 4.23 times 10 to the minus second molar. So we have these new concentrations of a weak acid and a conjugate base that we can have contribute to the acidity of the solution. So there's two ways that we can figure out the pH at this point. I'm going to show you the first way is to use an ice table, which will always work. But since we know we have a weak acid and a conjugate base in solution, we can skip the ice table and solve for pH directly using the Henderson-Hasselbalch equation. So I'll show both of them here. So if we need to think about what's happening in terms of an equilibrium between these, I'm going to write this from the acid standpoint because we're given the Ka value. So we're going to use the Ka value. The Ka value, again, is 1.3 times 10 to the minus fifth. The equation for Ka is going to be our weak acid finding a water molecule, giving up its proton, and leaving behind the conjugate base. So our ICE table that we have here has 1.43 times 10 to the minus second. Water's not part of our equilibrium. We're going to assume negligible concentration of H3O plus from any other sources, and then 4.23 times 10 to the minus second. Just like we always have numbers in our reaction tables, we always have variables in the change column of our ice tables. So in this case, we're going to lose some of this, gain some of this, gain some of this. And 1.43 times 10 to the minus second, x 4.23 times 10 to the minus second, plus x, minus x. Now, again, we're going to assume that, and we already did our pre-check, that this equilibrium constant is small enough that our x's are going to be small. So what we really can say is that our weak acid concentration is equal to 1.43 times 10 to the minus second, and our conjugate base concentration is equal to 4.23 times 10 to the minus second. That's going to become important when we do our Henderson-Hasselbalch equation in a minute. But let's go ahead and just put this into our Ka expression, making our assumptions. Right? We're assuming that x's are small, so these values just go in as this. Ka is equal to 1.3 times 10 to the minus 5. So if we solve for x, going ahead and solving for x, x is going to give us ultimately pH, and pH is going to give us 5.36. So again, you can go through this with an ice table, but again, I want to show you using the Henderson-Hasselbalch equation how we could do this. And I encourage you, if this makes sense, to go ahead and do it for our weak-strong combinations. The Henderson-Hasselbalch equation is pH equals pKa plus the log of the conjugate base concentration over the concentration of the weak acid. So we have pKa, which is going to be the negative log of our Ka value, 1.3 times 10 to the minus fifth, plus log of the concentration of our conjugate base, 4.23 times 10 to the minus second, 1.43 times 10 to the minus second. Again, this is going to be a value that is greater than 1. Okay, so this is going to increase the pH. Negative log of this value is 4.886. Mathematically, this value works out to 0.474, and the pH that we get is the same thing as if we used an ice table, which is 5.36. So again, a lot of information that we went through there fairly quickly, but we're always going to be using the same steps. Ask who's in solution and who does chemistry. Strong base rips a proton off of a weak acid. Use a reaction table to figure out the number of moles of species that remain after the chemistry is complete. Use the new volume to convert those numbers of moles into concentrations. Put those concentrations into an ice table and solve for this X, which again is going to be H3O plus, which we can use to get pH. Or if you know you have a weak acid and its conjugate base, you can use the Henderson-Hasselbalch equation to solve for pH. Okay, so let's kind of map that onto our cheat sheet here for our weak-strong combination. Again, if we're at point number 2 before the equivalence point, we used an ICF table, and from there we determined the moles of HA and A minus and divided by the total volume to get our new concentrations. So that's what we just talked about here, getting our new concentrations. The suggestion here on the cheat sheet, which is truly the shortest way to go about doing this problem, is understanding that before the equivalence point, with a weak-strong combination, we're always going to have a buffered region where we have a weak acid and its conjugate base. Since we know we have a weak acid and its conjugate base, we can use the Henderson-Hasselbalch equation to solve more directly for pH, which we did down here. All right, we're going to move on to next how we figure out the pH at the equivalence point. So this was part B.